Ladies and gentlemen, let's bring our hands together for Scott Meyers.
Thank you very much. I can see it's going to be an excellent talk, since the first thing that happened was that the person introducing me emphasized how old I am. Thank you very much for that. That's what happens when you hire a professional. He also emphasized my extensive background in C++. Thank you for that. This talk is not about C++. This talk is about something which is more fundamental than C++. This talk is about the hardware. I want to talk about CPU caches because this is what is ultimately going to determine the performance of your program. It does not matter what programming language you are using. It does not matter what application you are trying to develop. It doesn't matter any of that stuff. At the end of the day, the hardware determines what is going to happen. We need to understand how the hardware works. I want to start with a very simple problem. Let us suppose we have a matrix, and what we want to do is visit every element of the matrix, maybe to find out how many non-zero elements we have, perhaps to add up the total number of values in the elements. There's two basic ways that we can traverse this matrix. We can go row by row. This is known as a row major traversal. It visits every element of the matrix exactly once. We can go column by column. We can, as a result, we'll also visit every element of the matrix exactly once. Both traversals do exactly the same amount of work. They visit the same number of memory locations, they just do it in a different order. Furthermore, if you sit down to write the code for a row major traversal or a column major traversal, you will find that the code is almost identical in both cases. So if we want to do a row major traversal, we simply have a nested for loop, and the rows are on the outer loop. The columns are on the inner loop. If we want to do a column major traversal, we simply reverse the order of the loops. Columns on the outside, rows on the inside. So conceptually, we're hitting exactly the same amount of memory, exactly the same number of times. Writing the software is trivially different if we want to do a row major versus a column major traversal. What is interesting and what concerns us is the resulting performance is not that similar. What I did here was row major and column major traversals of matrices of various sizes using two different compilers. One of them happened to be GCC, one of them happened to be Microsoft C++ compiler. These lines here correspond to column major traversals. Given that this is time, higher lines are worse. Column major traversals are taking noticeably longer than row major traversals. The other thing I want you to notice is the column major traversals don't proceed in a linear fashion. There's this little leg in here. This is a row major traversal using using Microsoft's compiler. This is a row major traversal using Microsoft's compiler. Now, I do not want you to conclude from this data that Microsoft's compiler sucks. I mean, you might conclude it anyway, but that's not what I want you to conclude. What I want you to conclude is that if you have two completely independent compilers that have the same kind of behavior, that suggests that there's something more fundamental going on than just compiler optimization. Notice that the row major traversals scale linearly with the size of the matrix and are substantially faster than the column major traversal. And what this tells us is that traversal order matters. We'd like to understand why. But before we address that question, I want to raise a new question based on a different observation. So instead, let's talk about scaling for dealing with counting the number of odd elements of a matrix. So here I have a square matrix, and what I'm going to do is count the number of odd elements, so the number of odds is set to 0. Then for every element in the matrix, I simply find out whether it's an odd number, and if it is, I increment it. Works fine, gives us the right answer, there's no issues here. Except, I took this example from a blog post by Herb Sutter. And Herb Sutter doesn't do serial algorithms anymore. Herb Sutter is Mr. Concurrency these days. So this is just a baseline. What we really want to do is scale this by throwing more threads at the problem. Because if you think about it, if I have giant matrices, it's silly to have one matrix running through the entire thing when I can have one thread running through the entire thing, when I can have n threads running through the entire thing. So this is from the same article that Herb published. And let me give you some insight into the difference between writing code that is designed to be presented in a presentation such as this, and writing code that is designed to be read by somebody reading a magazine article. Here is something you should notice. I have an array of integers of size p. That's because I'm going to have p total threads. Then what I'm going to do is for every element lowercase p. Now this is the thing. If you're going to have a presentation that's oral, you don't normally have uppercase p and lowercase p in the same presentation, because it is difficult to distinguish orally. So for every thread p of the p threads that we have, you can tell this was written for a magazine article. This is what we're going to do. We're going to take this matrix and we're going to break it into strips of roughly the same size. Then what we're going to do is turn a different thread loose on each one of those strips. So each thread will then work in isolation, counting the number of odd elements. After every thread has finished counting the number of odd elements in its strip, we will add all those numbers together. That will give us the total number of elements that are odd in the matrix. So we're just setting up the threads here. This is actually pseudocode. This isn't even legal in C++11 or C++14, but it is a lambda. And if you read through here, what we're doing is we're just figuring out where is the beginning of the thread strip, where is the end of the thread strip, and then this is where the work starts. From the beginning of the strip to the end of the strip for this particular thread, if it's an odd number, I'm going to increment the slot that I have in the results array. There are p total threads. Each thread has its own individual slot in that array. So as it's counting how many elements it's seen that are odd, it will write that value into its individual element of that array. And then we'll wait for all the threads to finish, set the number of odds to 0, add up all the values that are in the array, and we'll be done. It's the straightforward way to parallelize this algorithm. And I'm going to show you Herb's results rather than showing you my own results because this is kind of embarrassing. Herb has a machine with 24 hardware threads, and I don't. It makes me feel kind of inadequate. So this is the data that Herb published. So this is with one thread. So if you have one thread, which is the serial version of this algorithm, this is how fast it runs. That's set to 1, because all we care about is how fast are things compared to single-threaded. So now we throw another thread in, 2 threads. With 2 threads, immediately performance drops by over 40%. That is the kind of scalability result we are looking for when we are writing concurrent algorithms. But that's okay, because we have 24 threads. We will keep throwing more and more threads at the problem. So 3, 4, 5, 6, 7, 8. Well, finally when we get up to, I believe it is, looks like about 16 threads, we are now running at a whopping 10% faster. That's what we like to see. 16 times as much CPU power, and we are getting results 10% faster than before. Outstanding. But remember, we have 24 of these babies. So we keep throwing more and more at it, so by the time we get to 20 threads, we're running a whopping 40% faster, 20 times as much CPU power, running 40% faster. So then we keep throwing more threads at it, and it actually starts running slower. This is not ideal scalability. However, let us suppose we make the following very small change to the source code. We still have the global array, which is going to keep track of how many odd elements each individual thread finds. What we're going to do, though, is for every individual thread, it's going to declare its own local counter. We're going to set that to 0. And then when it finds an odd number in the matrix, instead of incrementing its array element inside result, we're going to increment its local counter. And then, after it has counted everything in its strip, we will take the local counter and we will assign it to the array element. Everything we know about software says this should have worse performance. It uses more stack space because we have a local variable for every one of those threads. We're using more memory. We are making an otherwise unnecessary assignment from this local variable into the array. We're doing more assignments than we did before. Everything about this algorithm says it should be worse. And here is the scalability. The result is perfect scalability. Everything said it should run slower. It runs vastly faster. And what that tells us is that thread memory access matters. We'd like to understand the answer to that question as well. And what it all boils down to is CPU caches. The reason that we had differences between row major and column major traversal performance is because of CPU caches. The reason that we get much better scalability using a local variable rather than using an array is because of CPU caches, which means we better understand what CPU caches are. CPU caches are simply small amounts of unusually fast memory. That's all they are. They generally hold the result of recently accessed memory locations, although not always. There are three common types of CPU caches. First, there is the data cache, also known as the D cache, sometimes known as the D $sign. It holds data. There is the instruction cache, also known as the I cache or the I $sign. It holds instructions. And just about the time you were getting comfortable thinking, okay, caches are called cache, there is the translation look-aside buffer, known as the TLB. It's also a cache. The translation look-aside buffer caches the results of translating from virtual pages into real pages in systems that use virtual memory. So it's caching the translation from a virtual page address to a real page address. I'm not going to talk any more about TLBs in the remainder of this talk because if you find ways to take advantage of the behavior of the data cache and the instruction cache, pretty much automatically your TLB usage will also improve. So you don't need to think about that too much specifically. If you talk to people who've been involved in the caching effects on systems, and if you read about them, you will find quotes such as this one. This is from Sergey Solyanik from Microsoft, Nokia, Microsoft, I don't know. So, Linux was writing packets at about 30 megabits per second wired and wireless at about 20. Windows CE, that's the Microsoft product, was crawling at barely 12 megabits per second wired and 6 megabits per second wireless. In other words, the people at Microsoft said, damn, those open source people are beating the pants off us. We hate that. We found out that Windows CE had a lot more instruction cache misses than Linux. Notice, this is not talking about the data cache. This is talking about the instruction cache, which tends to be the cache that most people don't focus on. But right away, we're seeing that can make a big difference. The quote continues, after we changed the routing algorithm to be more cache local, we started doing theta 35 megabits per second wired and 25 megabits per second wireless, 20% better than Linux. So from Microsoft's perspective, a success story. From our perspective, an interesting insight that by changing an algorithm simply to take better advantage of the instruction cache, we can get dramatically improved performance. This is from Jan Gray. He's on the Microsoft performance team. And in case you wonder why I keep quoting Microsoft people, it's just because they blog a lot. And as a result, it's easier to get that information from them. What he says is if you're passionate about the speed of your code, it is imperative that you consider the caching and the memory hierarchy as you design and implement your algorithms and data structures. This is talking about the data cache. And speaking of the data cache, my favorite quote actually is from Dmitry Vukov. He wrote Relacy Race Detector. Cache lines are the key, exclamation mark. Undoubtedly, exclamation mark. If you make even a single error in the data layout, you will get a factor of 100 slowdown, exclamation mark. And in case you think he's joking, no jokes, exclamation mark. The man is serious. Virtually all modern architectures for mainstream platforms, and that includes mobile devices, these days have hierarchies of cache. They don't have one cache. They actually have different kinds of hierarchies of caching. I'm going to be talking, because I wanted to give something specific, I'm talking about the Intel Core i7-900 series processor. The reason I chose it is very simple. That happens to be what's in my laptop. It is representative of what 3 years ago, when I bought my laptop, was a pretty high-end processor, and these days is a decent middle-end processor. This particular processor, it has 32 kilobytes. 32 kilobytes. Anybody remember kilobytes? Not megabytes, not gigabytes, 32 kilobytes of level 1 data cache per core, and 32 kilobytes of level 1 instruction cache per core that's shared by 2 hardware threads. 32 kilobytes. Look it up. It's not much. 256 kilobytes of level 2 cache for every core, holds both instructions and data, however, so in some sense it's bigger, but it's smaller because it's now sharing instructions and data, also shared by 2 hardware threads. And finally, we get to level 3 cache. Level 3, finally, 8 megabytes. That's the big one, 8 megabytes. Individual photographs these days are pushing 8 megabytes. That's the entire cache, but it holds both instructions and data, and it's for the entire system. In this particular case, on this processor, it's shared by 4 cores, which is 8 hardware threads. This is the same information, except it uses pretty pictures and colors. The caches are not to scale. It's just to give you an image of the caching hierarchy. So in this case here, we have 4 cores on the machine. Every core has 2 threads. There's the level 1 instruction cache, the level 1 data cache. There's a level 2 cache with attached instructions and data, which finally goes to the level 3 cache, which is shared by all 4 of these things. And in case you forget, somewhere out in the big, wide, wonderful world, there actually is main memory somewhere. That's where your gigabytes are located. But as we shall soon see, nobody cares because it takes so long to get there, your program will not run at any reasonable speed if you go to main memory. I told you before that CPU caches are simply small amounts of fast memory. So when I tell you that CPU caches are small, we're talking, as an example, let us assume that for this particular architecture which I introduced, you have a 100 megabyte program image, which in many circles is not a terribly large image. That's your 100 megabyte runtime image, code plus data. So what that means is 8% of that will fit in the level 3 cache, and that's the big cache, remember that. But the level 3 cache is shared by every running process, including, I might point out, the operating system. So you do not have 8 megabytes of level 3 cache for your own use. You are sharing it with everybody else. Even if you are the only process running, there is probably an operating system, and the operating system is using it as well. The level 2 cache, 1/4% of your image will fit in the level 2 cache. 3/100% will fit in the level 1 cache. So it's not big. And when I say they're fast, so again, for this particular architecture which I've been talking about, the level 1 cache latency is 4 cycles. The level 2 latency is about 1/3 as fast, 11 cycles. Level 3 latency, about 1/3 the speed of that, 39 cycles. Main memory latency is 107 cycles, about 3 times slower than level 3. Which means it's 27 times slower than level 1. If you run a program profiler to find out where you are spending CPU time on your program, most program profilers count a CPU as being 100% busy if it's waiting for an instruction or from data to be delivered from main memory. And what that means is potentially you can have 100% CPU utilization according to your profiling tool while the CPU is spending 99% of its time idle. This is the same information here in graphical form, although I have found that you can look at numbers like this and you kind of intellectually grab them, and you can look at charts like this and you kind of intellectually grab them. But I attended a talk recently where Mike Acton showed an animation, and I just want to show you the relative speed of fetching memory from the various caches. So this is a level 1 cache transfer of memory. That's level 1. That's level 2. That's level 3. I'm so glad there's a place to sit. Let's take a look at main memory. This is to scale. This is how long it takes to access main memory. Oh, we're still going. I should have brought a book. Implication is, from a speed perspective, the total amount of memory in your system is the total amount of cache. Main memory is so slow to access. Practically speaking, you might as well assume it's not even there if you have any kind of performance constraints on your program whatsoever. So on this particular machine, the one I've been talking about, the Core i7-900 series, 8 megabytes of fast memory, and if you noticed in that last animation, it wasn't that fast when we got to the level 3 cache. That's for everything. It turns out on this particular architecture, everything in L1 and L2 is also in the L3, so you can't even add the 3 caching hierarchies together. 8 megabytes, that's the total amount of memory that you have on this particular architecture. The details vary from architecture to architecture, but this is still not unrepresentative. So this is what we know. Small is the same as fast. How many people studied computer science? Excellent. How many people learned when they studied computer science about the time-space trade-off? Almost no one. That's so pathetic. It turns out that the hardware never went to school. It has no idea about a time-space trade-off. At the hardware level, small is fast, and that's as simple as it gets. Which means compact, well-localized code that fits in cache is fastest. We're talking now about instructions. So people have probably heard over the years, you probably should make your code small, not to have too many branches, don't call too many functions. This is why you want it to fit in the cache. Compact data structures that fit in cache are going to be fastest, and data structure traversals that touch only cached data are going to be fastest. When you have to go to main memory, either for instructions or for data, there will be a long stall in the processing of your program. Caches are organized into what are known as cache lines. Conceptually, we think that if we want to get some data out of the memory, we say, go and fetch me this, let's say, word from memory. But that's not how the memory system works. What happens is, if you ask for 1 byte, you get a cache line. And a cache line on the Core i7 system is 64 bytes. 64-byte cache lines very common these days for Intel and AMD processors. And to put things in perspective, 64 bytes, that means 16 32-bit values. So if you are dealing on an architecture, for example, with 32-bit integers, that means 16 of them will fit on 1 cache line. If you have 64-bit values, 8 of them will fit on 1 cache line. And main memory is read and written in terms of cache lines. So if I request this 1 byte here, that's the only byte I care about, this entire cache line will be brought in from memory. If on this cache line I write this 1 byte, this entire cache line will eventually be written out to main memory, which means you want to be using as much of the cache line as you possibly can. This actually tells us right now why a row major traversal is faster than a column major traversal. So with a row major traversal, I come to the first element here. Let's suppose it's not in memory. So I wait around for that unbelievable 107 cycles to read in the first element of the array from main memory. But when I do that, I automatically get the subsequent elements. So I had to wait for this first one, but the rest of these were already in memory, which means I went zipping down that cache line, and I was able to calculate whether they were 0 or non-zero right away. Now, I might get a cache miss here, but then I get to go fast again. With the column major traversal, if I get a cache miss here, I read in the entire cache line, which I then ignore, because now I go to the next line down here. And then I go to the next element, and I go to the next element, which means with a column major traversal, you are likely to run into cache miss, cache miss, cache miss, cache miss. Whereas with the row major traversal, you're running right down the cache lines. And in fact, the hardware is designed to detect patterns of access and to speculatively prefetch cache lines it thinks you might need. So if you do a forward traversal through a cache line of line n, the hardware will start prefetching cache line n plus 1. And it goes in the other direction too. If you are going backwards through a cache line, the hardware will detect these access patterns and will speculatively prefetch things, which means that going linearly through memory in either direction is the most cache-friendly thing you can possibly do. Any kind of data access or instruction access that fits that pattern will run faster than anything else. Which means, first, locality counts. So if I do a read or a write at some address A, that means that the contents near A are probably already cached, either because the address near A was on the same cache line as A, so when A got dragged in, the other address near A got dragged in as well, or we were in the middle of a forward traversal or a reverse traversal, and when we brought in the cache line for A, the hardware speculatively prefetched the cache line which had this other address that was near A. So now we know why small and fast go together when it comes to the hardware. We also now understand, because of this speculative prefetching, predictable access patterns matter. The hardware actually is smart enough so you don't have to be accessing every individual element of a cache line. If you're going every 2 elements, every 3 elements, every 4 elements, as long as there's a regular, predictable stride, there is a reasonable chance the hardware will notice what you are doing. It does this on a per-thread basis, and will start prefetching cache lines for you. So linear, predictable access patterns that are consistent with forward and reverse traversals through cache are the best you can possibly get. And this means, from a data structure point of view, that linear array traversals are extremely cache friendly. Of all the fancy data structures in the world that you can come up with, the one the hardware likes best is an array. The lowly array is really what the hardware is very fond of. It has great locality, it's a predictable pattern, it has great traversals, and this means that a linear array search can beat a binary search of a heap-based binary search tree, because heap-based binary search trees have to chase pointers, which means you get lots of cache misses. While you are waiting 107 cycles for a pointer to have been dereferenced, you can read through an awful lot of cache lines linearly. Exactly. A binary search of a sorted array, if I could have made that noise, I would have, can beat a O of 1 search of a heap-based hash table. Now, for those of you who study computer science, I have good news. I studied computer science as well. Computer science is valid. Big O wins for large N. When N gets large enough, then suddenly the cache effects become less important than some other effects. So if you're dealing with data structures of really large size, for example, if you're Google, or if you're Facebook, or any place else with giant amounts of data, you reach for hash tables immediately. But when you are running, for example, on a smaller data set, maybe a subset of something that you found in your hash table, you go back to dealing with these kinds of issues here. So that's the basic story with caches. But let's talk a little bit about what happens when you have multiple copies of the same data in different caches. Again, with the same architecture I've been dealing with, let's suppose I've got core 0 and core 1, and some thread running on core 0 has accessed some memory location, and therefore it has been brought in from main memory, and it now happens to find itself in the L2 cache on this cache line. So this is the data, whatever it happens to be. Could be an instruction, could be data. Let's assume it's data. But let us assume that core 1 is also running a thread, and on this thread, it also happens to have accessed that cache line. In particular, it happens to have accessed that same data element. We now have 2 copies of the cache line in the hardware. Let's assume that one of the threads on core 0 now does a read or a write. Actually, let's assume that core 0 does a write to this location. And let's assume that core 1 does a read from this location. Now, this is truly proceeding concurrently on the hardware. So the question is, what value does core 1 read? Does it read the old value that core 0, before core 0 wrote it? Does it read the new value? Does it read some weird mixed up thing because it turns out it happened to get a snapshot of it when 2 bytes of the old value had been written, but 2 bytes of the new value had also been written? I have really good news for you. Well, here's the news. If, as software developers, you had to worry about this and take manual steps to eliminate these problems, you would all go raving insane. You'd have to try and figure out, how can I make sure that all the values are coherent across all possible distributions of caches across all the hardware we care about. But here's the good news. You get a programming model from the manufacturers of the hardware. The programming model says that caching is a latency-reducing optimization, and that you as a software developer don't have to worry about it. And it's true, you do not have to worry about it. Here's the situation. There is only one virtual memory location with the address A, and it only has one value. That's your programming model. The fact that on the hardware, it could be in main memory, in level 3 cache, in 4 possible copies of level 2 cache, and in 4 possible copies of level 1 cache is not your problem. That's the problem for the hardware designers. And what happens is, in the hardware invalidates cores 1 cached value when core 0 does the write. It all happens automatically. You don't need to worry about it. Probably. If you are programming with multiple threads, you're always told you must avoid races. Now, a race is when you have 2 or more threads accessing the same memory location, at least one of which is a write, and there's no synchronization. Everybody's taught, don't do that, it's bad. There's various ways to avoid it. For example, the most common way, use a mutex. The mutex will make sure you can't have 2 threads simultaneously accessing the same memory location. No race. Second thing is use an atomic instruction or an atomic variable. Available in most programming languages, available on virtually all hardware. That'll solve the problem as well. So, as long as when you are programming, you make sure you have no data races, the hardware will take care of the problem. Now, let us suppose you don't follow the rules. Let us suppose you say, I'm not going to use a mutex. Let us suppose you forget to use a mutex, or you forget to use an atomic instruction. Now you have a data race, and it probably in the past has been extremely frustrating if people said, if you do this, results are undefined. This is why results are undefined, is because it is extremely difficult to predict what the hardware is going to do if you truly have concurrent access to different copies of the same thing in main memory at the same time. The reason your programming language can't tell you what's going to happen is because it honestly does not know. So that's why the rule of the game is that as long as you synchronize access to shared data, so you use mutexes to make sure you're not accessing things simultaneously, you use atomic machine instructions, something to make sure that there is a way to prevent individual threads from simultaneously accessing the same memory where one of them, or at least one of them is a writer. As long as you do that, the hardware takes care of everything else. That's the only requirement that falls on you. So that's the good news. You follow the rules, you will not have to worry about the cache coherency problem. But it's not free. The hardware has to execute, for lack of a better term, instructions. It has to have electrons running around making sure that you see a coherent picture of memory. So what you would prefer to do is to avoid running into cache coherency problems in the first place. Not because you'll get the wrong answer. You'll get the right answer as long as you synchronize everything. You won't get the right answer as quickly as you otherwise would. Let us assume, so core 0 is accessing some address A, and core 1 is going to access some address A plus 1. Now, there's no race here. Address A is completely independent from address A plus 1. You don't need to use a mutex, you don't need an atomic machine instruction, everything's fine. But it is highly likely that address A and address A plus 1 fall on the same cache line. And remember, cache lines are the currency that is exchanged between main memory and the caching system. So let us suppose that here's core 0, it happens to have this cache line in it, and it's accessing address A on that cache line. Here is core 1, it happens to have a copy of the same cache line here, it's only accessing A plus 1. When core 0 does a write to address A, the entire cache line is marked dirty. In particular, it's marked dirty in all the other caches. So when core 0 does a write to its copy of the cache line to address A, then through the magic of hardware, this cache line in this L2 cache here is marked dirty, which means it's no longer valid. So when core 1 decides to write to A plus 1, what happens is we discard this cache line, we go back out to main memory, we grab it in, we wait 107 cycles for it to be pulled in. It comes in here, we then write to A plus 1. When we write to A plus 1, that marks this cache line dirty. And remember, I am showing you 2 cores of a 4-core machine. So Any write to any copy in cache will invalidate all of them on the same CPU. And if you're dealing with a multiprocessor, where you've got multiple circuit boards in there, where you've got maybe 4 cores on each board, you've got 4 boards, you've got 16 cores, you write to one cache line, and that copy of the cache line is invalidated across your entire system. And it takes a while for the electrons to get from one circuit board to the next. You will get the right answer, but it will take longer than it should. From the memory subsystem's point of view, you are sharing memory, even though you're not really conflicting. This is known as false sharing. False sharing is what occurs when you have access patterns to memory next to one another or near one another so that they fall on the same cache line, but they don't conflict. And if we go back and take a look at the Herb Sutter issue we saw before, so here's Herb's original code for doing concurrent access. So we have this array of p integers. It's going to be laid out in memory as a contiguous chunk of memory. It'll stretch across one or more cache lines. Under the assumption that we have 16-bit integers on a 64-bit cache line, that means you're going to have 16 individual counters on the same cache line. Now, down here, I have p threads simultaneously incrementing their own counters. And look what I'm doing. It's a plus plus. That's a read, modify, write operation. From our perspective, what makes it important is it's a write operation. Because it's a write operation, when any thread does a plus plus, it will mark that entire cache line dirty across all other caches that are in the system. And as a result, you'll get the right answer here, but you're probably churning through memory much, much faster than you need to be able to. And it's going to be worse the larger the number of odd elements in the matrices, which means if you have a few matrices which have very, very few elements, the scalability will be great. You change the data, so you've got more odd numbers in the matrix, suddenly the scalability will fall off a cliff, and you will probably have no idea why. That explains why the fix works. If we now put if we give every thread its own counter like this local counter is going to be on a per thread stack frame. And the stack for this thread is not going to be on the same cache line as the stack for this other thread over here, which means every individual thread is going to get its own counter, and it'll be on its own cache line. So now I've got all these threads doing plus plus count on their local counter. I no longer am running into false sharing, which means I'm not going to have this scalability problem. Now, at the end, I still have to write this local variable into this array, but I only have to do that once. So that's not going to be a big bottleneck in most cases. And it's worth reminding ourselves what the results are. So with false sharing, the fastest we ever got was a 40% speed up, and that was with about 20 times the number of threads as a serial traversal. If instead we eliminate false sharing, we get perfect scalability. This is why false sharing is important. And it's purely a CPU cache issue. In order to have a problem with false sharing, the following things must all simultaneously be true. First, you have to have independent values or variables that happen to fall on a single cache line. False sharing is when you have independent chunks of data that are manipulated independently and they happen to be on the same cache line. And you have to have different cores concurrently accessing that cache line. Remember, false sharing is a problem of cache coherency. So if I have only one thread or even two threads on the same core accessing the data, because there's only one copy of that data in one cache, I don't have to worry about marking other cache lines dirty in other people's caches. So it's only when you're dealing with multiple cores. With multiple cores accessing the same cache line. Frequently. If it only happens every once in a while, trust me, there's lots and lots of other ways to slow your programs down. So false sharing is not likely to be a problem unless you actually have to access those cache lines frequently enough that the resulting slowdown is noticeable in the overall behavior of your software. And at least one of them is a writer. One of the nice things about computer science that hasn't changed is you can still have as many threads simultaneously doing reads as you like. That's not a problem. It's only when you have at least one writer that there's going to be an issue. Any kind of data is susceptible. For example, statically allocated data like globals and statics. Now, I realize nobody here would ever consider using a global variable, but think about the people who are not at the conference today. If you declare a global variable, it's got to be laid out in memory somewhere, which means the compiler might say, okay, here's a global variable possibly declared in a different translation unit, and the compiler might decide, or the linker might decide, I'm going to put them right next to one another. Perfectly legal for the compiler and the linker to do. And if that happens to happen, and they're manipulated independently, you can have a false sharing issue. Statics can have the same issue. File static, class static, function static, things that are local in anonymous namespaces. Basically, all data that has static storage duration has to be laid out somewhere. It's generally packed together because you don't want to spread it all over through memory and waste a lot of memory. And as a result, it is possible that you're going to run into a situation where two completely independent pieces of data that have nothing to do with one another happen to end up on the same cache line. Heap allocated data. I dynamically allocate a small data structure here. I dynamically allocate a completely different data structure over here. It's entirely possible that at runtime, they happen to end up sharing a cache line. If one of them is not large enough to fill an entire cache line, the other one could get stuck in to fill part of the remainder of the cache line. Even automatic variables and thread local variables can lead to false sharing problems if you hand out pointers and references to them. Because if you hand out pointers and references to them, now you can have multiple threads all accessing the same memory at the same time. I would love to be able to tell you there is a really simple solution that eliminates all false sharing problems. You won't have to worry about it. If there is such a solution, I am unaware of it. It is simply one of those things you have to learn to look out for. For people who program in unmanaged languages like C and like C++, after a while you begin to develop a certain degree of intuition. So if your program starts doing various impossible things, you begin to recognize, oh, okay, that looks like you're probably overwriting an array somewhere, you've got a wild write or a wild read, some kind of memory corruption. You just begin to recognize what it looks like. With false sharing, if you have a system that seems like it should be scalable and it's not scaling the way you expect, after a while you'll begin to get an intuition that goes, looks like it could be a false sharing problem. And then you have to sort of poke around a little bit further to try to figure out whether that's the cause of the problem or not. There are tools that can help, but they're not great. Another quote from someone at Microsoft. During our beta 1 performance milestone in parallel extensions, which is their library for parallel algorithms that shipped with the CLR, most of our performance problems came down to stamping out false sharing in numerous places. And in some sense, the scariest thing about this quote is most of the performance problems. Now, it could be, it's entirely possible that the reason that was the majority of their performance problems is because they had a really good team together that had done a really great job of otherwise preventing performance problems from arising. Or it could be that that's not the case. So at this point, I want to step back a little bit and sort of summarize where we stand with what we know right now. So the first thing is small is the same as fast. Or I suppose from our perspective, fast is the same as small. From a CPU caching point of view, the only thing that really matters is does it fit in cache or does it not? There isn't a time-space trade-off at the hardware level. The second thing is locality counts. You want to try to stay in the cache whenever you possibly can, both for instructions and for data. And predictable access patterns count. You want to try to be prefetch friendly. You have probably heard that if you write code that doesn't have a lot of function calls, doesn't have a lot of loops, doesn't have a lot of branches, it will run faster. You now know why that's the case. It's because, remember, if you're reading through cache lines of instructions, the hardware will prefetch the instructions for you. So if you have straight line code that just goes running from top to bottom, no branching, that's perfect for reading from the instruction cache. So let me try to give you a little bit of guidance before we cover one more thing. First, for data. Wherever it is practical for the problem that you have to solve, you want to employ a linear array traversal. I hate to say it, but I'm sorry. When it comes down to the hardware, the only data structure that is important is the array. There's other issues which can enter into your overall decision making, but at the hardware level, really it loves arrays. I was talking to the CTO of a man who was working for a financial firm. They do algorithmic trading. Algorithmic trading companies are the kinds of companies that, depending on your point of view, either provide very necessary worldwide liquidity to the financial markets or are driving us into absolute economic ruin, depending on the way you look at things. But what this man told me is, he goes, look, I don't know what your fancy data structure is, but I know that an array is going to beat it. That's not always true, but it's true often enough that it's worth bearing that idea in mind. Basically, hardware loves arrays. The second thing is, you want to use as much of a cache line as you possibly can. Bruce Dawson, who used to work in Microsoft's Xbox division for people making video games is an interesting industry, actually, because you have to refresh the screen either 30 or 60 times a second. And given that frequency, it tells you just how many milliseconds you have to get everything done. It's a hard deadline. And what he said was he would often look at a program which didn't have the refresh rate, the frame rate that they wanted to be able to have, and he'd find something like this. So I've got a struct object, and these are video games. Things tend to get blown up or destroyed or killed or otherwise mayhem occurs. So it was not uncommon to have a Boolean called something like isLive. This might be a bit field, it doesn't matter. And then there'd be a vector, let's say, of objects. So I'd have a big giant data structure of all the objects in the game. And then what we would say is, well, okay, for every one of the objects that exists in this game, if the object is alive, I want to do something with it. But if the object is not alive, I don't want to do anything with it. But think about what that means from a caching point of view. So what that means is, I read an object in here, and I'm going to assume for purposes of this discussion that the size of the object is at least 64 bytes, just because that's one full cache line. The only reason I'm making that assumption. So you read in an entire cache line, which corresponds to an object. You check the Boolean. If the Boolean is false, you immediately discard the entire cache line and move on to the next object. This means you are using 1 bit, essentially, out of 64 bytes worth of information. In fact, he told me that at Microsoft, in the Xbox division, they had a special tool which basically would tell them for every individual cache line what percentage of it was accessed before the cache line was flushed out of cache. And if you saw the number was really low, 2%, 5%, he knew right away what the problem was, even without having to look at the data structure. So that was kind of interesting. And it leads to the notion of what is called data-oriented design. How many people have heard of data-oriented design? Okay, there's a few people. It's received a lot of publicity and a fair amount of traction, especially in the video game industry, where, like I said, they have these very stringent real-time constraints. And essentially, what it boils down to is laying out your data structures in memory in a way that will make the CPU caches happy. And in this particular case, for example, what you would say is, you don't put a Boolean indicating whether an object is alive inside the object. Instead, what you do is you have a separate data structure consisting of bits indicating whether individual objects are alive. So when you read in 64 bytes worth of information, you now know how you have at least 64, you have the information for at least 64 objects, whether they're alive or not, and if you use bit fields, it's 8 times that. But what this means is, the fundamental idea of object-oriented programming. Object-oriented programming. We take the data, we take the functions, we bring them together so that the system makes sense, so programmers can make sense of it. Object-oriented programming. And now we say, we take the objects and we take the data and the instructions, and we now start taking the data and we pick it apart and we parcel it out because the hardware doesn't like objects. This is the whole idea behind data-oriented design. I'll give you some references for more information. It is specifically designed to get the most value out of every individual cache line that gets read. And let's just say you're not going to have a Boolean inside an object. I'll refer you to a talk by Mike Acton where he actually says one of his anti-patterns is if he ever sees a Boolean in a struct, he knows right away it's wrong. He doesn't even care what it does. Which at least makes it easy to identify. And finally, we're talking about data. You also want to be alert for false sharing in multi-threaded systems. Look for suspicious lack of scalability. So that's data. There are also instruction caches. It is equally important to take instruction caches into account when you're trying to make the best use of the hardware. So the first thing is you want to make sure you're going to fit the working set in the cache. This has some interesting consequences. Let us suppose you were dealing with an object-oriented system, and you have some base class, and then you've got 3 derived classes. I don't care what the base class is, but I've got derived class A, derived class B, derived class C, whatever they happen to be. So I have a container of all the objects in the system. In C++, it would be a container of pointers, but we don't care. So I've got a container of heterogeneous objects. I've got subtypes A, B, and C, and then I have some virtual function, some dynamically bound method called process. And now what I decide I have to do is I have to process every element of the system, every object in the system. So what do? All right, so I go to the beginning of the container, I get the first object, I pull it off the container, and I say, okay, I'm going to call process on it. I call process. That's a dynamically bound call. We try to figure out, is it an A, a B, or a C? Let's assume it's an A. Great. We go down. We now need to invoke A's processing function. Well, we just started this, so it's probably not in the instruction cache. No problem. We go to main memory. We swap in all of the instructions for executing A's processing function. Great. We're done. We go to the next element of the container. Because this is a talk about pathology, the next type is a B. We go down into the subtype B. Oops, we don't have a copy of its processing function. So we swap all the instructions for its processing function into cache. We execute them. Great, we're done. We go to the next element. Of course, it's of type C. So we go down to execute C's processing function. We have to bring all the instructions from main memory into the instruction cache. Damn, the instruction cache is too small. It won't fit everything. Something has to go. What do we get rid of? We get rid of all of A's processing function. It's been a long time since we executed that. We go back to the next element. Of course it's of type A. Not a theoretical problem, by the way. And it is, as a result, very common in systems that can't afford that to actually sort their sequences by type. They won't have a container of all the objects in the system. They'll say, this is the A's, this is the B's, this is the C's, and they'll traverse each one of them one by one, simply to make better use of the instruction cache. I've also seen other designs where they have a complete container of all the objects in the system, but they sort them by type. All the A's are in the front, all the B's are in the middle, all the C's are at the end, specifically to avoid this kind of problem. I have mentioned before that what you want to do is get rid of branches. So what you would like to do is make the fast paths branch-free sequences. So what you want to do in many cases is, if it's a critical path of your program, check for all the oddball cases that are not normally common up front, make those non-inline function calls, and then drop through to straight-line sequences of instructions, which the CPU cache and its prefetcher will be able to help make a lot faster for you. Speaking of inlining, the good thing about inlining is it reduces branching. A function call is a branch. Probably leads to an instruction cache mish. So, reduces branching. That's good. It also turns out that inlining facilitates other kinds of optimizations by the compiler that simply yield smaller code. Basically, when compilers have more context information, they're able to perform better optimization decisions. The bad thing is, with an inline function, you say, okay, here's the body of the function, I'll put it in my code here. Here's the same function, I'll put it here. Same function, I'll put it here. Now you have the same instructions, more or less, strewn across various parts of your program, which makes your overall program image larger, and what that does is it reduces the effective cache size, because you might end up with 2 different copies of the same inline function in your instruction cache at the same time. Fortunately, there is a better set of tools for dealing with some of these issues, in particular PGO and WPO. How many people are familiar with PGO? PGO stands for Profile Guided Optimization. It is a mode in virtually all modern compilers where what you do is you take your source code, you give it to the compiler then generates code in the usual fashion, except the generated code is instrumented so that at runtime it'll be able to keep track of exactly what happens. You then run that executable on representative use cases, the ones you want to optimize for. You then recompile, and the second time that you compile, the compiler takes not just the source code as input, it also takes all the data that it collected when it was being run on those representative use cases, and it feeds that into the compiler, so the compiler can say things like, oh, I see at this particular branch location, you went this way 99% of the time. I'm going to have that be the fall-through branch. I see that when you called this virtual function, you called this particular class's function 99% of the time. I'm going to inline that right below this point. I'll still check to make sure it's the right function, but the point is I won't have to go off and get the instructions. So what PGO does is it permits the compiler to generate better code. On certain kinds of programs, PGO can have dramatic effects on performance. It can make the program run 15 to 20% faster. I'm not going to say that's common. However, I will say that if I were writing a performance-sensitive program, and I knew that there was the possibility that I might get, let's say, a 10 to 15% performance improvement simply by building it in a different way, I would probably look into it. WPO is whole program optimization. It tends to complement profile-guided optimization. These tools here, which are almost certainly in your compiler, assuming at least that you're using a C or a C++ compiler, can automate a lot of this information here. We haven't had a huge amount of time to talk about CPU caches. We could go on for a long period. So I want to talk about some things I haven't talked about. I didn't really talk about the memory banks of caches. I didn't talk about associativity, but I will in a second. I didn't really talk about exclusive versus inclusive content in caching. We didn't really talk about hyperthreading. We didn't talk about evaluating the performance of caches. We didn't talk about cache-oblivious algorithm design, which is a general design mechanism that allows you to produce software that should take advantage of whatever cache you have available, regardless of how much cache is available. They tend to be divide and conquer algorithms so that they recursively invoke themselves, and eventually the subproblems get small enough that they'll all fit in cache. But it's a basic approach to design designed to run well on many kinds of hardware. But instead what I want to do is talk a little bit about overall cache behavior. And we're unfortunately losing some lines here in the projection. These are all supposed to be matrices, so all the boxes are supposed to look like that. So just imagine these are all matrices. It doesn't matter. My only point here is, first, if I have a matrix with a certain number of elements, 10,000 elements, 1,000,000 elements, 52 elements, it can be in so I can have different sizes, and within a particular size, the shape can vary. So it turns out the area of this matrix, the area of this matrix, and the area of this matrix, they're all the same, but obviously the number of rows, the number of columns vary. So if you have a particular matrix, it can vary in size, or it can vary in shape. So what I did 3 years ago was I sat down and I said, I'm going to experiment with matrices of different sizes and different shapes just to see how long it takes to traverse them. So what you're seeing here is this is the overall size of the matrix. This is how many columns it has, so it gives you some idea of what the shape is. And then this is how much time it took. And all I did was read every element of the matrix. That's all I did. And all I wanted to know was how long does it take me to do that? This is for a row major traversal. Now, with what I've told you, we'd expect a row major traversal to basically take about the same amount of time for a fixed size matrix because of prefetching and regularity of access patterns, which means that we'd expect this whole thing to be basically a plane. Now, it's not completely planar, but it's pretty close. And it's possible that while I was doing the work, I might have been bored and been reading email or surfing the web. Maybe. Anyway, it's pretty close to planar. It matches our expectations. So this is the same data for a column major traversal. And I know what you're all looking at, but that's not what I'm going to talk about. Because what's more interesting, frankly, is what's going on right in here. I mean, this is sort of planar over here, but this is kind of wacky. So what I'm going to do is I'm going to take a slice through this data where the number of columns is equal to 200. And it looks like this. Now, this is a column major traversal. The number of columns is fixed at 200, so the shape is fixed, basically. And this is the size of the matrix. If this doesn't make you think that the world is just insane, you're not looking at it closely enough. Because what this says is, if I have a 21 megabyte matrix, I should make it bigger so that I can traverse it faster. If I have a 26 megabyte matrix, I might as well pad it to make it 27 or 28 megabytes because it's going to run a whole lot faster. This is not explained by any of the stuff that I've talked about so far, and yet, this is the data. It is because what I haven't talked about yet is what is known as cache associativity. Our mental model for the way caches work is that it's a little chunk of memory, and so when I read a cache line from main memory, I can put the cache line into the cache. That's the mental model. And that's not how it works. It turns out that for most caches, the way it works is when the hardware reads a cache line, it looks at the address of the cache line, and then the address of the cache line determines exactly which slots in the cache it can go into. An 8-way associative cache means for every individual address, it can go in at one of 8 different locations. A 4-way associative cache can go into any one of 4 locations, which means if you are so unlucky as to choose addresses of cache lines that are conflicting with one another, where they all have to go into, let's say, one of the same 4 slots or the same 8 slots, suddenly your cache isn't this big, it's this big. And there's a blog post that was done by Igor Ostrovsky, and for our purposes, all we care about here is that in this chart down here, white is fast and blue is slow. So he set up arrays of various lengths, and these are the step factors. The step factor is how far do you take a stride before accessing the next element of that array. And what you find out, for example, with, let's say, a 8 megabyte array, so it starts out slow. Remember, blue is slow. Slow, slow, slow. Now it gets faster. Suddenly, right here at 256, it's slow again. Faster again. Suddenly at whatever that number is, I can't see right now. Slow, fast, slow, fast. Notice what happens at 512. It turns out that 512 is a horrible, horrible step factor for almost every matrix size. And the reason this is interesting is because it is not uncommon for programmers to say, I need to choose a number, maybe to hold something, maybe I'll be hashing things, maybe it'll be the size of an array. I'm not sure, but I'm a computer person, so it should probably be a power of 2. I think I'll choose 512. And if your step factor happens to be 512, at least when he did these experiments, you are completely hosed. It's just going to be slow because of the cache associativity effects. So if you wanted to really understand what's going on with caches, you'd have to certainly cover associativity effects. So that's the end of what I'm going to talk about, but as I said, there's a lot more information that you could acquire. When I have questions about how CPU caches work, the very first place I go is this document here, What Every Programmer Should Know About Memory by Ulrich Drepper. It's 7 years old now, which seems like it should be ancient history, but it's still very accurate as far as I know. Now, when it says what every programmer should know about memory, I'm not sold. He starts with transistors. I skipped that part. I wanted to do something a little bit more abstract, but in terms of, if you want to know how caches work, how do cache lines get invalidated, what's the exact protocol, how long does it take, how do you write experiments, that's what you want, is what every programmer should know about memory. Igor Ostrovsky's chart I just showed is from the Gallery of Processor Cache Effects. That's this blog post here. There's some other references here. The PDF will be made available, so you don't have to worry about writing all this stuff down. Herb Sutter's article on false sharing was Eliminate False Sharing, and I just like the title of this one, False Sharing is No Fun. Kind of says it all. This is a blog post talking about this idea of batching per type virtual function calls. As I said, not a theoretical problem. I mentioned data-oriented design. If you're interested in the whole idea of how would you lay out your data structures so that you can get the most out of the CPU, Mike Acton gave a very nice talk on this at CPPCon. That was in September of this year. The video is available at YouTube. I mentioned profile-guided optimization. Lots of references on profile-guided optimization because I am a believer. See, 2 pages worth. I am a believer. There's some stuff on whole program optimization as well. And I think that is that. So that is the conclusion of the presentation. Thank you very much.
Thanks so much, Scott. I think we've got just several minutes left for questions. By the way, the question, how old are you, doesn't count. What I was referring to was that Scott probably learned to program in C++ before he learned to walk or talk.
Nice backpedal.
Over to you, ladies and gentlemen. Questions, please.
Hello.
One over there, please, unless somebody's already got a mic.
Oh,
okay. Oh, gentleman over there, and you, sir, will be next, please.
Hello. I've got 2 questions. The first one is about code qualities. When one is concerned about writing readable code, testable code, one which takes care of proper dependencies and encapsulation, can those code qualities coexist with the with all the changes that we need to make to write code which is cache friendly, or rather beyond some point we need to sacrifice them to really achieve the best of performance? And the other question is there a need, and we can experience proliferation of the cache friendly algorithm and design patterns, also those which are focused on the data? Can we experience proliferation of such algorithms and design patterns, or rather each time we have to work on those problems, but on a each case-by-case basis to achieve the best performance? Thank you.
So let me answer your second question first. If you're interested in reading about basically algorithm design that will take advantage of cache without having to redesign the algorithms every single time, that sub-area is called cache-oblivious algorithm design. There's an entry for it, for example, in Wikipedia, but you can fire up your favorite search engine, search for cache-oblivious algorithms, and you'll get lots of reading on how to go about doing that. As for your first question about the resulting readability of the code, what I would actually recommend that you do is to go back and take a look at Mike Acton's talk, because like I said, it's available on YouTube. Fundamentally, what he argues is that it is part of the job of a software engineer to get, in his case, as much performance out of the hardware as possible. And his argument is that by taking data that naturally is used together, and for example, putting it into a struct or a class so that it'll be on the same cache line, that actually makes it easier for people to reason about, if I change this, what effect is that likely to have on performance? So his argument is, and his experience, I believe, as a professional software developer, has been that by focusing on these issues, you actually end up with systems which are easier to read about and are easier to maintain. They don't look like classic object-oriented systems, because they don't bundle everything together. But his argument is that if you bundle everything together, it becomes impossible to reason about the performance characteristics. So assuming that you wish to be able to reason about the performance characteristics, he argues, and I believe it's a legitimate argument, that there is nothing contradictory about taking into account how the hardware behaves and also organizing your code in a readable fashion. Okay?
Gentleman over there, please.
So I have a short comment and then a question related to this comment. If you would really like to read a book during your animation, then you could add a database. My question is that when you deal with databases, then you're really happy when you can fit your data into main memory. You don't think about caches. But the principles you were referring to seem to also be relevant to working with databases. So maybe could you comment on that?
All right. The first thing I will say is if you take a look at the implementation of a database query system, trust me when I tell you they are caching up the wazoo. And there are companies that do nothing but cache things that come from databases. So caching is simply an optimization to hide latency that is inherent in the application. And I'm talking about, for example, caching between main memory and the main part of the application. But people also use caching, for example, to minimize network delays. They use caching to minimize days, assuming you're using physical disks. But as I said, in the database world, one of the major things they worry about is what to cache and how long to cache it. So the specific issues of CPU caches, very extensively used in database query optimization systems, and the more general concept of caching as a latency reduction mechanism, also really high on the list of database implementers. So definitely relevant.
Shall we get just one more question? That side of the room, you've been awfully quiet. Okay, a question over there, please.
Okay.
Gentleman there.
I have a question about what we can do more about optimization. For example, how can we prevent some cache, the cache to be cleaned out by other data? For example, if we use a read-only array like a lookup table and we want to be sure it will stay there in the cache, can we do some additional steps to keep it there? Or I believe it's like a first in, first out basis with the cache. How can we make sure it will stay there?
Okay, the first thing I will remark on about your comment about first in, first out on the cache. In the CPU caches, it's not first in, first out, and it can't be because of this associativity effect. So as far as I know, the caches don't try to do first in, first out. So I could be mistaken, I could look it up later, but I know they can't just get rid of the oldest thing because they can't necessarily use that cache line. Okay. So the more general question about, I want to make sure I've got something, I want to stick it in cache, and I want to make sure that it absolutely positively stays there. I think that on some hardware, there are instructions which allow you to pin things in cache. I don't know of any programming language that gives you direct access to that as a language feature, but then again, I don't know any programming languages that actually let you talk about the hardware caches. Generally speaking, the idea is that if you have, let's put it this way. Your idea was, I want to take a lookup table and I want to pin it in cache so it's fast to access. If you have this lookup table and it really is fast to access, and it's really accessed a lot, it's naturally going to stay in cache anyway because it's being accessed very, very frequently. On the other hand, if you pin it in there thinking it's going to be frequently accessed, but it's actually not accessed that frequently, you may actually be artificially reducing the size of the cache for other data that would be accessed more frequently. So I would be reluctant to go down that path unless I had some data that told me that I really know that this lookup table needs to be pinned here and it's being evicted for some reason. Does that help a little bit?
Yes, thanks.
Okay.
Okay, can I have just two more questions, please? The gentleman over there was first in line, and then over to you, gentlemen, please.
Okay, I have one question about profilers instrumentation. So you talk about profilers, and my question is, do they have some side effect? Because profilers also use memory, and do they somehow assure that they use different part of memory and they don't have conflict with main application with which they profile?
Okay, is the question whether compilers take steps to avoid false sharing when they're laying out the data? Yes. As far as I have never heard of a compiler trying to determine when false sharing would occur and then trying to prevent it from taking place. With a normal compilation model where the compiler has no idea what data is going to be used simultaneously by different threads, I think this would be fundamentally impossible. With profile-guided optimization, it could collect information that could be useful in that area. I haven't heard of PGO being used for that, but that's the first place that I would look to find out whether compilers do that. Having said that, at least in the realm I'm familiar with, which is C++, I would proceed on the assumption that compilers will be no help whatsoever in preventing false sharing. And I'm sorry about that.
Okay.
Yusa over there, please.
Answering question here, you said that this is the task of developer to adopt to hardware architecture and caching performance, yeah? Mm-hmm. But on the other side, also hardware change differs between vendors and between product lines and changes over time. So how to deal with this? Any advice here? What are the general concepts and what are the differences usually?
Okay. Clearly, the details of hardware change over time. At the same time, for the foreseeable future, I think it is safe to assume that for mainstream hardware platforms, you're going to have a hierarchy of caches, and the general stuff we've talked about is going to continue to apply. The size of the cache line might change. It might go from 64 bytes to 128 bytes, for example. The number of hierarchies might go from 3 levels to 2 levels on some processors or to 4 levels on some other processors. But I think the basic idea of compact data structures that are linearly traversed will be the most cache-friendly. That has been true for many, many years, and I expect it to be true for many, many more years. I simply haven't heard of anything coming along that's going to make that a false assumption. And similarly, instruction streams that don't have any branches in them, I think is going to continue to be true for certainly the next 10 years. I just haven't heard of anything changing other than that. The other thing I will mention, which I didn't talk about, is that the relative speed of CPUs and memory, conceptually speaking, memory is getting slower and slower compared to the increase in speeds of CPUs, and that is unlikely to change. And what that means is that it is more important now to make good use of CPUs than it was 10 years ago, and it potentially will be even more important in the future. Basically because processors are getting faster, not necessarily with clock speed, but they're able to execute multiple instructions on a single cycle. That's increasing in speed faster than latency on memory is being reduced. Does that help a little bit? Okay.
Thank you, Scott. Scott will be back later this afternoon. I've always thought that cache is one of the most important things in life, but after this talk, I'm tempted to think that caches are even more important. But Scott's point is that good caches are good for your cache, so bear that in mind. Scott Meyers.
Thank you. Thank you very much.